Okay, so let's scoot on. Let's talk about polynomial functions and models. In this particular section, we have a lot of definitions and theorems to go over, so hang in there, and we'll get to some examples as we move through these. So let's look at the first definition. The first definition is with respect to a polynomial function, and here's what the definition says. A polynomial function is a function of this form. Now, this form looks extremely familiar to us. We're like, okay, so what's so special about this? Well, let's make sure that we're all on the same page. A sub n minus 1, a sub all the way down to a sub 1, a sub 0, these are all the coefficients. With me? And then we have x to the nth power, and n minus 1, and all the way down to 1, and x to the 0. So clearly it's in descending order as well, right? Okay. Now, x to the 0 power is what? Yeah, it's just 1. So technically, this last term is the constant. Now, here's the deal, though. When you first learned about polynomial functions, you may not have learned the full definition. Here's the full definition of it. This is part of it. Here is the rest of it. So, a sub n to a sub 0, these are our coefficients, we said, right? And this little symbol means member of, part of, belongs to. So all the coefficients are real numbers. You with me? So they can be any real number in the world. Positive, negative, fractions, decimals, whatever. Is I a real number? Yeah, no, so they can't be I. Good. Second thing, n, which is the power here, correct? And this is also a power because it's n minus 1 all the way down. So n is a non-negative integer. So non-negative means it has to be what? Yeah, positive. So you're like, well, why don't they just say positive? Well, here's the deal. Not only does it have to be positive, it has to be an integer. And you got to remember what an integer is. And sometimes it's easier to say what's not an integer. So an integer is not equal to a fraction or a decimal. So in other words, your powers can't be fractions and they can't be decimals. And non-negative means they need to be positive. So get that as well. Cool? And then the last part of this definition says the domain of this polynomial function has got to be all real numbers. The domain, negative infinity to positive infinity. I have to be able to use all of these numbers. I can't kick anybody out. With me? Okay, so hang in there. I'll be right back with some examples that we're going to decide if they're polynomial functions. Okay, so notice the directions. They want us to know, or they want us to tell them if these four are polynomial functions. Remember, to be a polynomial function, the coefficients have to be real numbers, right? To be a polynomial function, the power has to be non-negative and it has to be an integer, right? Lastly, the domain has to be all real numbers. Agreed? Okay, so let's take a look at number 1. So, first things first, right? So, we have to check for the coefficients. Are the coefficients all real numbers? Yes, this is a 4, this is a 1, these are real numbers. Check. The second thing we have to make sure of are the powers. Are the powers non-negative? Well, yes, this is a power of 1 and that's 3. They're non-negative. And they have to be integers. Remember, an integer is not a fraction and it's not a decimal. So are these two powers okay? Check. And last but not least, we have to make sure that the domain is good. The domain has to be all real numbers. In this particular case, would you be kicking any numbers out? Or could I use any number I wanted for those x's? Remember those red flags we talked about? Good. Check. So yes, in this particular case, this is a polynomial function. Okay, let's look at number 2. Same thing. We have to check for coefficients. We have to check the powers. And we have to check the domain. So the coefficients are 3 and a negative half. Are those real numbers? Check, that's good. Check the powers. Well, there's only one x and it has a power of 1. That's non-negative, and it is an integer, isn't it? Check. And is my domain good? Do I have any red flags there? No red flags, we're good. Check, I can use anything I want for x. So, is this one a polynomial function? Yes, this one is a polynomial function also. Okay, let's look at number 3. Same thing, we have to check the coefficients, we have to check the power, and we have to check the domain. So, are the coefficients good? Are the coefficients real numbers? Well, that's a 1, that's a negative 1, it's still real, and a 2. So yes, check, that's good. Got to check the powers. They can't be negative. Well, these are not negative, and they have to be integers, excuse me. They have to be non-negative, and they have to be integers. Are they all integers? Nope, they are not. You see where it failed? Right here it failed. That doesn't work for us. This is crossed off. This is no, this is not a polynomial function because one of those powers was a fraction. And remember, an integer is not a fraction and it's not a decimal. So number 3, that's not a polynomial function. Good? Okay, so let's check number 4. Same thing, we've got to check for our coefficients, we have to check for our powers, and we have to check for our domain. So, coefficients, are they good? Yeah, they're good. The coefficients are good. They're positive. They're all real numbers. We're good. Powers. Powers okay? Yeah, technically the powers are good. So check. Lastly, the domain. Is the domain all real numbers? Can I use any number I want? Yeah, no, this one failed. Because this guy in the denominator says can't be equal to 0, which means my domain is not intact. Which means this is a no. This is not a polynomial function. Are you with me? Cool. Hang in there. Be right back. Okay, so let's look at another definition. This definition is with respect to a real 0. So let's read it. If f is a function and r is a real number, remember that little symbol means a member of, part of, for which f of r equals 0, then r is called a real 0 of f. So, one of the things to notice is this is an if-then statement. If these are true, then here is the result. So let's look at the if again. F is a function and r is a real number. So those two things need to be in place. And the third thing is that when you plug r into f, you get a 0. You plug r into f and the whole polynomial goes to 0. The whole function goes to 0, I should say. Good? If those three things happen, then r is called a real 0 of f. Well, here's the deal. There's some results that happen from this definition. So let's look at them. Here's one of the results. Let's talk about this a second. If you plug r in, r would be what variable? Yeah, r would be the x, wouldn't it? Because you're plugging it into an f of x. So r would be the x. And when you plug in this number for x, you end up with 0. 0's for which variable? Y. So here's the deal. You plug a number in for x, you get a y equaling 0. Get a number for x, plug a number in for x, y equals 0. What did you actually just find there? What is that? When x is a number but y is equal to 0, what is that? Yeah, it's an x-intercept, isn't it? So one of the results is r is an x-intercept. You with me? Okay, here's another item that I'd like you to notice. Let me back off and give you an example over on the side here. So let's say you had x equaling 4, x equaling -3, and just, x equals 0. These are your solutions that you got, okay? Here's what I need you to do. Need you to think backwards a moment. X equals 4. What was the equation that was right before it that you said, oh, well, of course x equals 4? Yeah, wouldn't the equation have been x minus 4 equaling 0? Right? And if x equaled negative 3, well, what was the equation that gave you that result? Yeah, that would have been x plus 3 equaled 0, wouldn't it? And this one, well, that's just x, isn't it? That's just an x equals 0 still. Okay, so question, keep thinking. These three separate equations came from what step before it? What did this look like before they got split out into three different equations? There you go. It looked like this, didn't it? And I'm going to stick the x in front over here, equaled 0, didn't it? It came from this polynomial, didn't it? Right? And this polynomial, this is a factored form, isn't it? This factored form came from a polynomial that looked like this. Right? And then one more step, it actually came from this third degree polynomial, didn't it? So here's what we're used to. We're used to starting here with this third degree polynomial and then finding our x's, solving, aren't we? So here's the deal. If we're used to starting here and we're working these steps, these x's are also the solutions to this particular polynomial, isn't it? Well, there's a second result. R is a solution to f of x equaling 0. It's also a solution. Are you with me? And one last result is this. This is your R. This is where it came from. Agreed? If this is where it came from, this equation came from us doing this factoring, didn't it? So here's the thing. This x minus 4 would be a factor of this third degree polynomial, wouldn't it? Okay, so hear what I said then. That means that x minus r is a factor of that function. You with me? 3 results based upon this definition. Cool? Okay, hang in there. I'll be back with another. Okay, so let's look at another definition called multiplicity. So it's in 2 parts, but when I know one part, the other one also makes sense. So let's read the first part. If r is a 0, and we just went through the definition of a 0, correct? It could be an x-intercept. It could be a solution, right? It could, anyway, you got the picture. If r is a 0 of even multiplicity, then the graph of f touches the x-axis at r since the sign of f of x does not change from one side of r to the other. You're like, what the heck? Okay, so r is a 0 of even multiplicity. So r is a solution of even multiplicity. Give me an example of an even number. Yeah, 2, 4, 6, etc., right? So let me throw an example up here. Say we have f of x equaling x minus 3 quantity squared, right? Okay. If I went to solve this for x, what will we get x equal to? Yeah, you would get x equaling 3. Twice as a matter of fact, because you would have x minus 3 written twice, wouldn't you? So you'd get 2 solutions, but they're the same, so they're duplicate, right? But this 3 is a solution twice. That's the even multiplicity part. So that means the graph of f touches the x-axis at that solution. Why? Because the sign of f isn't going to change from one side of r to the other. If I plug in a 2 here, what's 2 minus 3? Yeah, negative 1. And you square it, you get positive 1, don't you? But what happens if I plugged in a 4? So if I plug in a 2, it's on this side of the 3. If I plug in a 4 on the other side, what's 4 minus 3? 1. 1 squared is 1. It's not changing. The sign is not changing from one side of the 3 to the other. This is what it means why it's going to only touch the x-axis. Good? Okay, let's look at the second half. The second half is saying is R is a 0 of odd multiplicity. Okay, so odd numbers, yeah, 1, 3, 5, good. Then the graph of f actually crosses the x-axis at R, since the sign of f does change from one side of R to the other. Let me give you an example. What happens if it was just f of x equaling x minus 3? Right? I get a solution. If I solve this, my solution would be x equaling 3. Correct? But it only appears once. So this is why it's odd, because it only appears once. Now, if I took the number 2 and the number 4 like I did above, if I took the 2 and plugged it in, what would you get? Just -1, wouldn't you? If I took the 4 and plugged it in, what would you get? +1. The sign is changing from one side of the 3 to the other, which is why it's going to cross the x-axis in this particular case. Cool? Okay, hang in there. I got a couple of theorems that we're going to work with, and then we'll get into some examples that'll tie a lot of these definitions and things. Okay, so let's look at 2 last theorems before we get into some examples that'll tie these all together. The turning point theorem. F is a polynomial of degree n. That's all the if says. Well, that's easy enough. Then f has at most, and yes, I purposely left it blank. So here's what I need you to think about. I need you to get a parabola pictured in your head. Got it? That's a second degree equation, correct? How many times does the graph turn? Yeah, it turns only once, doesn't it? It makes one turn and it goes back up the other side or down the other side, right? So a second degree polynomial has one turn, right? Okay, I need you to think of a third degree polynomial. Remember what shape that is? And if you're not sure, let me draw it. That's that funky little S shape, isn't it? Okay, if this is a third degree, how many turns does it have? Yeah, it's got 2 turns, doesn't it? A third degree, 2 turns. A second degree, 1 turn. Now, a fourth degree, you may not know what it looks like, but I think you may have actually had to do it on your graphing calculator in a previous lecture. It actually has like a shape of a W. And so now the question is, how many turns does this fourth degree have? It has 3 turns. So, if f is a polynomial of degree n, then f has at most n minus 1 turns, which is why it's called the turning point theorem. Cool? Okay, let's look at this last theorem, the end behavior theorem. For large values of x, and these values could either be positive or negative, the graph of f behaves like y equals a sub n times x to the nth power. And then they tell me a sub n is the leading coefficient and n is the degree of f. So you're like, well, what does this mean? All right, so hang in there. Let me give you f of x equaling, I don't know, 2x squared plus 3x minus 1. What's this the graph of? It's a graph of a parabola, right? A parabola going which direction? Yeah, a parabola going up. What told you it was a parabola? The x squared. What told you it was going up? The 2. This first term told you it was a parabola and it told you it was going up, didn't it? The rest of it makes the inside of the parabola move around, but it was only the first term that told you that it was a parabola, right? So you know that this one is going to have this shape to it. In the middle may change, but it's still going to have this shape basically. The ends are going to look like this, right? They're both going to go up. Agreed? Okay. What happens if I gave you, let's say I gave you this particular function? What will this be the graph of? This is also the graph of a parabola, isn't it? Going which direction? Down. How did you know that? What told you? Yeah, the first term had an x squared, told me as a parabola. The lead coefficient was negative, which told me it went down. Now this plus 4 is going to move it around a little bit, but only the first term told me that it was a parabola going down. So the ends are going to behave like this. The ends are both going to be going down. The middle is going to change, but not the ends. Are you with me? That's the deal for this end behavior theorem. It's telling you if you really want to know the shape of the polynomial when you graph it, you really only need to look at the lead coefficient and the degree of the polynomial. Cool? Okay, so hang in there. I've got some examples. Okay, so let's look at these directions. They would like us to find 4 things for these two polynomials. They'd like us to find their zeros in multiplicity. They'd like us to find if the graph touches or crosses at that x-intercept. They'd like to know the maximum number of turning points, and they'd like to know the end behavior. So let's look at this first one. So first off, they want to know what the zeros are for this particular polynomial. So we need to find the zeros. We need to find their multiplicities. And part B wants to know if it touches or crosses. Right? Okay. So let's check it out. Remember, the zero is a solution to the polynomial, right? The zero is also known as an x-intercept. So here's the thing. This polynomial is already in factored form, is it not? Which means I could take each one of these factors and equal it to 0 to find those solutions, to find those real zeros, couldn't I? So if I took this parenthesis of x minus 7 and I set it equal to 0, what would I get? I would get 7. What's the power on this factor? Yes, it's a 1, correct? All right. What's another 0? This parenthesis says x plus 3. I set that equal to 0, I get negative 3. Awesome. Okay, so my zeros are a 7 and negative 3. Now I need to know their multiplicities. I need to know how many times they actually appear as a solution. Well, the 7 came from x minus 7. That has a power of 1, right? Which means the multiplicity is, good. This is a multiplicity of 1, which means it's odd. The negative 3 came from the parentheses of x plus 3, but this has a power of 2 on it, doesn't it? Which means this actually appears how many times as a solution? Yeah, twice, which means it has an even multiplicity, doesn't it? Now, according to the definition we had before on multiplicity, if it's an odd multiplicity, is it just going to touch the x-axis or is it going to cross the x-axis? Yeah, odd multiplicities cross the x-axis. What about the even multiplicities? They touch the x-axis. Cool? Good. Part C wants to know the number of turning points, which means you need to know the degree of this polynomial. Now think about it. If this is a power of 1 and this is a power of 2, this polynomial has a degree of, good, this is a degree of 3. So, maximum number of turning points would be, I heard you, good, 2. With me? Last one wants to know the end behavior. So, remember what we said before, the end behavior, and I even showed you some examples. Might help if I spell it correctly, right? Okay, so the end behavior has to do with you looking at the entire polynomial? That's right. No, not the entire polynomial. Sorry. So it doesn't have you looking at the entire polynomial. It has you looking at the lead coefficient, which would be 3, and the power, which we already said was a third power. This has an end behavior of 3x to the third. Good? Okay, so let's look at number 2. Same questions. They want to know the zeros, they want to know their multiplicities, and they want to know if they touch or cross. Let's take care of those first two. So, here's a parenthesis, x squared plus 1. Okay, so I got to set that equal to 0 and solve, don't I? And when I set this 0 equal to 0 and solve, I get the square root of a negative 1. Is that a real number? Because this gives you plus or minus I. That's an imaginary number. So does this give me a real solution, a real 0? Nope. So there's no real 0 coming out of this first one. So forget that one. How about the second one? Yeah, that's a 2 coming out of there. And since that's my only 0, what's its multiplicity? Good, it's a multiplicity of 3, which means it's odd. And it is going to cross. Good. Yeah, that parenthesis, that factor of x squared plus 1, that one we have to be careful about. That gave me an imaginary answer. That's not so good. Okay, they want to know the maximum number of turning points. I guess we need to know the degree, right? Well, now think about it. Even though this factor didn't give me a 0, it still has a power of 2. And this has a power of 3, which means this polynomial has a degree of 5. So what's the maximum number of turning points? 4. And I need to know the end behavior. Okay, so remember the end behavior has to deal with the lead coefficient. In this case it's 4. And it has to do with the power, which is x to the 5th power. Good? Okay, hang in there. We're going to work backwards. Okay, so now they've given us a graph and they're asking us to find the polynomial that goes with this graph. And you're like, oh, how am I going to do that? So here's the thing. We're going to work backwards. Remember on the last two problems, they gave us the polynomial and we could identify the zeros. And remember, 0 is another name for an x-intercept, right? Okay, so I can do the same thing here. I can identify my zeros, right? I can identify their multiplicity based on the fact if they touch or cross. So I'm seeing one 0 of negative 1, because that's an x-intercept, isn't it? I'm seeing another one of positive 1 and another one of 4. Now, the multiplicity on the negative 1, do you notice it touches? So that's even, right? Because it touched. This one crossed, so this is odd because it crossed. And this one crosses, so that means it's odd because it's crossing. So here's what I'm noticing. So far, I'm noticing my polynomial looks like, since this is minus 1, in the factor, it'll be x plus 1. Since it's an even multiplicity, the power could be a 2, a 4th. I'm just going to make it a 2. I'm not going to go to 4, 6, and 8. I'm not doing all those. Got it? Okay, since this is 1, that means it came from x minus 1. And since this is a 4, it came from x minus 4. And they both have odd multiplicity, so I'm going to leave them as powers of 1. Cool? Now, a lead coefficient. You're like, lead coefficient? How am I going to find the lead coefficient? Here, think about it. If I need to solve for a, then I better know x and I better know a y, because these are my variables. I have x's, I have a y, and I have a. If I want to solve for a, I better know x's and I better know the y. Do I? You're right. I do. Here it is. I have an x and I have a y. So, let's move over here and let's see about doing some work. We have x equaling 3. We have y equaling 8. Correct? So, y equals, that tells me 8 equals a, and in the parentheses, x plus 1. Well, since x is 3, how about 3 plus 1, power of 2? X minus 1, well, since x is 3, 3 minus 1, power of 1. X minus 4, well, I got 3 minus 4, power of 1, right? Okay, so let's keep working. What's 3 plus 1? Good, 4. Squared? Good, 16. 3 minus 1? That's 2. 3 minus 4? Negative 1. Okay, I know some of you had your calculators out. Hopefully you could do without your calculator. So I have 8 equals negative 32a. And when I solve for a, I get negative 8 over 32, which does reduce to a negative 1/4, doesn't it? You just found your lead coefficient. F of x would be equal to negative 1/4 in parentheses x plus 1 to the power of 2 times the quantity of x minus 1 times the quantity of x minus 4. You just found the polynomial that went with this function. Yay! By the way, I forgot to mention something in that last problem. The only reason we could find the lead coefficient is because they gave us that extra point, 3, 8. If they don't give me an extra point, if all they give me are my x-intercepts, I'm not going to be able to find the lead coefficient. Again, if all they give me are my x-intercepts, I can find the bulk of the polynomial, but I shall not be able to find that lead coefficient. The only reason I could find it was because they gave me the extra point of 3, 8. That's why I could find the lead coefficient. Cool? Okay, now you guys have fun with this stuff, and I'll catch you on the flip side.